Welcome to this professional training on chiller plant design and control. In this session, we'll explore how chilled water systems are designed, how their components interact, and how intelligent control strategies maximize efficiency and reliability. A chilled water plant's mission is simple: remove heat from the building and reject it to the atmosphere. But behind that simplicity lies complex engineering. To make this process work efficiently, 5 functional parts must work together: the chillers that generate cold water, the loads that absorb heat, the distribution system of pumps and piping, the heat rejection system, usually cooling towers or condensers, and the controls that synchronize the entire plant as one integrated system. Chillers are the heart of any plant. They can be air-cooled or water-cooled and operate on the vapor compression cycle. Inside every mechanical chiller, 4 components form the core: the evaporator, where water gives up its heat to refrigerant; the compressor, which raises the pressure and temperature of that refrigerant vapor; the condenser, where that heat is rejected to air or condenser-water; and an expansion device, which drops the refrigerant pressure before the cycle repeats. Some buildings use absorption chillers, which replace the compressor with heat energy, often from steam or waste heat, making them valuable for campuses with cogeneration plants. Evaporators are shell and tube heat exchangers where refrigerant and water exchange heat. 2 common types exist: flooded evaporators, where refrigerant surrounds the tubes that carry water; direct expansion evaporators, where refrigerant flows inside the tubes while water surrounds them. The efficiency of this process is defined by the approach temperature, the temperature difference between refrigerant and leaving water temperature. A smaller approach means better heat transfer. Flow rate is critical. Too high flow means erosion, vibration, noise, and control instability. Too low flow means laminar flow, poor heat transfer, and chiller trips on low temperature. Chiller manufacturers specify minimum, maximum, and allowable flow variation rates, often plus 10% per minute for standard controls, up to plus 50% for advanced systems. Condenser system, rejecting the heat. After absorbing building heat, the refrigerant must reject it. This happens in the condenser, and the method depends on the type of chiller. In air-cooled chillers, reject heat directly to outdoor air using fans. They are packaged, simple, and ideal for buildings without cooling towers. They work well in cold climates, offering year-round operation without freeze issues. Water-cooled chillers use a cooling tower to reject heat through evaporative cooling. Water at about 85 degrees Celsius enters the condenser, absorbs heat, and returns to the tower near 95 degrees Fahrenheit. Because the tower depends on wet bulb temperature, the condensing temperature can be much lower than in an air-cooled unit. Lower condensing pressure equals less compressor work and higher efficiency. At design conditions, a water-cooled system can be 15 to 25% more efficient than an air-cooled system, but requires water treatment, maintenance, and freeze protection. Every degree Fahrenheit change in condenser water temperature can affect chiller power by 1 to 2%. Raising condenser temperature increases compressor power, but can reduce cooling tower, fan, and pump energy. System optimization is about balancing all 3. From the comparison table, it is clear that air-cooled chillers are easier to maintain. Water-cooled chillers last longer and perform better, especially in humid climates. On the load side, chilled water cools the air through coils and air handling units. The control method determines both comfort and system efficiency. 3-way valves bypass unused water around coils, maintaining constant flow but wasting pumping energy. 2-way valves throttle flow, making the system variable flow and more efficient. Variable speed pumps can eliminate valves, controlling flow directly with motor speed. Face and bypass dampers regulate airflow, sometimes used for constant flow coils. A poorly balanced system with oversized coils or bypassed water may suffer from low delta T syndrome, a condition where the temperature difference between supply and return water shrinks, forcing chillers to handle more flow than necessary. That means higher pump power and reduced chiller capacity. Modern system controls constantly monitor delta T and reset flows to avoid this condition. Pumping and piping arrangements in chilled water system. There are three major hydronic configurations. 1. Constant flow system. Each chiller has a dedicated pump running at constant speed. It's simple but inefficient, since the same flow circulates at all loads. 2. Primary-secondary, decoupled system. This setup separates the chiller loop from the building loop with a bypass pipe known as a decoupler. Primary pumps ensure constant flow through the chillers, while secondary pumps vary flow to meet the load. This prevents unstable chiller operation, but adds cost, space, and pump energy. 3. Variable primary flow, VPF, system. The most modern approach. Here, a single set of pumps serves both chillers and loads. Flow through the chillers varies directly with demand, while a small bypass line ensures minimum chiller flow. This design uses fewer pumps, smaller electrical gear, and offers significant energy savings when properly controlled. Cooling tower and condenser-water system. In water-cooled systems, condenser water transfers heat from the chiller to the cooling tower. Key terms to remember. Range, the temperature drop across the tower. Approach, the difference between tower leaving water and outdoor wet bulb. As load decreases, both range and approach narrow, meaning colder water can be supplied back to the condenser. However, at low wet bulb temperatures, tower control becomes critical to prevent overcooling and freezing. Tower fans are often equipped with variable speed drives for smooth control. Proper chemical treatment prevents scale, corrosion, and biological growth, protecting long-term performance. Control and automation. Modern chillers are intelligent machines. Microprocessor controls continuously monitor chilled water flow, temperature and pressure, condenser water conditions, compressor discharge and suction pressures, oil levels, vibration, and refrigerant charge. Safety and diagnostics. Controllers protect against low temperature, high pressure, motor overload, and loss of flow. If water nears freezing, the controller automatically reduces compressor capacity to recover safely. System-level coordination BMS sequences chillers, pumps, and towers to minimize total plant kilowatt-ton. It also provides chilled water and condenser water reset strategies, dynamically adjusting set points based on load or outdoor temperature. Variable speed technology. Centrifugal chillers can use inlet guide vanes, IGV, or variable speed drives, VSD. While VSDs slightly reduce full load efficiency, they offer exceptional savings at part load, especially when tower water is cooler than design. A well-analyzed system can save 15 to 25% annually using drives on chillers, pumps, and tower fans. Design by system size, small systems, 1 to 2 chillers. Focus on simplicity. Air-cooled chillers with single-loop or variable primary designs minimize complexity. Wider delta T values can reduce pipe and pump size, cutting first cost. Often, these systems run unattended and use automatic enable-disable based on ambient temperature. Medium systems, 3 to 5 chillers, require smart sequencing. Designers decide between equal runtime rotation and preferential loading of the most efficient units. Variable primary flow and series arrangements become more common. Digital control systems coordinate pumps, valves, and chillers for stable operation. Large systems, 6+ chillers or district cooling. Here, hydraulic balancing, power availability, and long piping runs become design challenges. Systems often use series counterflow chillers, manifolded pumps, and multiple cooling towers. Control systems may be PLC-based with redundancy. Even a 1% energy improvement can save thousands of dollars annually. Energy and economic analysis. True optimization means looking beyond individual components. Lower chilled water temperature can increase chiller power, but reduce airflow and pump energy. Lower condenser water temperature saves compressor power but can raise tower fan load. Higher delta T design, meaning lower flow, reduces pipe size and pump horsepower. Modern software tools like Train Trace, System Analyzer, Energy Plus, and eQuest allow engineers to model these trade-offs using actual weather data, utility rates, and hourly load profiles. Always evaluate life cycle cost, not just first cost, especially when pursuing LEED certification or compliance with ASHRAE 90.1. Performance Monitoring and ASHRAE Guideline. 22. After commissioning, continuous monitoring keeps plants efficient. ASHRAE Guideline 22 outlines minimum instrumentation to track plant performance. Recommended daily metrics include outdoor dry bulb and wet bulb temperature, chilled water supply and return temperature, ton-hours produced, power input to each subsystem, chillers, pumps, towers, and overall plant kWW ton efficiency. This data reveals operational issues such as fouled tubes, low DT from coil bypassing, pump overspeeding, or inefficient chiller sequencing. Long-term trending supports predictive maintenance and helps verify energy savings for LEED or commissioning reports. Control platform choices, DDC versus PLC. Two main control architectures dominate modern plants: direct digital control, DDC, distributed intelligence, cost-effective, ideal for commercial buildings. If the main controller fails, local devices maintain safe default modes. Programmable logic control, PLC, centralized with fast processing and hot redundancy, common in industrial or district energy applications. The best system isn't about brand. It's about tuning, coordination, and commissioning. Smooth, steady control always beats fast, erratic response. Maintenance, reliability, and operational practices. Reliable operation depends on disciplined maintenance. Clean condenser and evaporator tubes annually. Maintain chemical water treatment. Inspect pumps, seals, and strainers based on manufacturer's recommendation. Verify sensor calibration and VFD set points. Review chiller trend logs monthly for anomalies. Preventive maintenance preserves efficiency, extends equipment life, and reduces emergency calls. Even small neglect, like dirty strainers, can raise pump energy by 10–15%. Integration with building system. A chiller plant doesn't operate in isolation. It integrates with airside systems, heat recovery loops, and sometimes even district heating. By coordinating temperature resets between air and water systems, buildings can maintain comfort at the lowest possible energy cost. Emerging trends include free cooling chillers, heat recovery chillers for domestic hot water preheating, and thermal storage for peak load reduction. These integrations elevate plants from mechanical systems to energy management ecosystems. Let's recap the core lessons. A chiller plant is an interconnected system. Efficiency depends on balance, not just machine performance. Proper flow management, delta T control, and sequencing are the foundation of efficiency. Variable speed drives and digital controls have transformed modern plants, but must be programmed wisely. Continuous monitoring and maintenance ensure sustained performance. The ultimate goal is lowest lifecycle cost with maximum reliability. A well-engineered chiller plant is not just a machine, it's a living, breathing system that balances performance, cost, and sustainability. Keep learning, keep optimizing, and remember, energy efficiency starts with good design and smart control. Thank you for joining this in-depth HVAC training on chiller plant design and control. If you found it useful, subscribe for future lessons on cooling towers, pump optimization, and system integration strategies.